And I'm Francesco De Vanna, for those who don't know me. I work with Giovanna at the University of Padova, and I'm mainly involved in numerical modeling and fluid dynamics of vortex-induced vibration for the assistant professor in machine fluid dynamics. As you are not all involved in fluid dynamics, it's intended as a general lecture about dynamic modeling and numerical model of cosmic-induced vibration devices. I start this presentation with a general introduction about flow modeling, and in general, everybody knows what a flow is. But modeling flows it's complex. It's very complex and requires a lot of expertise because the physics behind flow it's very complicated. It's inherently complicated. Here we can see two type of flows pertaining to the same environment. So it's a small river. The one on the top, it's very smooth, it's very shallow, but the one at the bottom, it's very chaotic and very complex as at first seen. So in these two scenarios, we distinguish two kind of flows. So the one on the top is known as a laminar flow. So the flow in such circumstances is flowing very smoothly and very regularly. On the other side, in this picture, we see what is called a turbulent flow. So a chaotic scenario of the same environment. So what is regulating these complex dynamics? So it's still water, it's still a river, but the dynamics behind the two systems is completely different. So historically speaking, this dynamic has been studied centuries ago, and in particular, we distinguish this dynamic as a function of the Reynolds number, which is the ratio between the convection of the flow scales inside the flow environment and the forces that are inherently inside of a flow, which are the viscous forces inherent in flow, because water has its own viscosity, of course. So if you ratio these two numbers, if you ratio the convection with respect to the viscous forces inside flow, you get a number, and this number allows you to distinguish between laminar flow, which are characterized by low Reynolds number, and turbulent flow, which are characterized by high Reynolds number. So what characterizes laminar flow? Laminar flow are characterized by the symmetry of their fields. So if we look at the fluid mechanics around a circular cylinder, that is an application very close to the intention of HO topic, we see that a laminar flow it's completely symmetric. So if you look at the value of the Reynolds number, we have Reynolds number very low Reynolds number 10, 20, 40, 70. And while increasing the Reynolds number, you see that the flow tends to lose their symmetric behavior. So in a case of very low Reynolds number, the flow is very smooth and very regular. And while increasing the Reynolds number, the flow starts to become chaotic. Okay. That's what happens in case of high Reynolds number flows. So the same cylinder, the same flow, it's still water, for instance, but you still increase the Reynolds number, and the flow behind the cylinder start to become chaotic, full of turbulent structures, and of course, increasing the value of the Reynolds number up to values that are consistent with application in engineering. So in engineering, we measure Reynolds number in the range of 10 to the power of 5, 10 to the power of 6, and that are the ranges which are even measured in HO applications. The flow behind the same cylinder becomes something like that. But the problem is, why in simulation you don't usually see such complex behaviors or such complex vortices and turbulent structures inside the flow? So if you look at the simulation me and Giovanna performed during the first part of the project, all the simulation looks like very smooth, the flow looks like very regular, and there are no structures like this one, for instance. So it seems why you are not replicating such complex dynamics. The reason behind this is that replicating a dynamic like this, it's extremely complex because all such structures, all these vortices could be even micrometrical. So you need to have a very high resolution in terms of your numerical model in order to catch a dynamic such a complex dynamics. So engineers has introduced what is called Reynolds decomposition. So you can think that your flow is composed by an average value. So for instance, the velocity of your flow is composed by an average value. So you average the velocity field through time, for instance, and you get the average velocity of your flows. And the real velocity is this average value plus a fluctuation that's, of course, it's time dependent. But in an engineering application, you don't need to know exactly what fluctuation is that number behind fluctuation, because you are not interested in general. You're not interested in fluctuation values, for instance, of forces, of pressure, and so on. But you are mostly interested in the mean value related to your flow. And that's why you introduce the so-called Reynolds-Averaged Navier-Stokes problem. So instead of solving the entire dynamic of flow, you just solve the average dynamic of the flow. That is what you are interested in, what you are looking for. I don't want to enter too much into the detail, but if you apply the Reynolds-Average decomposition to the Navier-Stokes equation, that are the equation behind the fluid mechanics, you obtain an unknown terms that is so-called turbulent stresses. So turbulent stresses is what that distinguish what is the complex, the whole complex dynamics related to a flow with respect to the average field. So instead of looking at the whole complex dynamics, you include an additional term that freezes all the complex dynamics you have and relies to you to compute just the average field. But of course, turbulent stresses are unknown, and it's a very big issue in order to model this term. And people tends to model it via a lot of hypotheses. And in particular, they suppose that all the turbulent structures inside a flow are isotropic, homogeneous, and so on, introducing what is the so-called turbulent viscosity, that is a parameter that must be modeled in some way. And that's why the model of turbulent viscosity are so complex. So hypothesis, in order to reach the solution of the average dynamic of a flow are very important, are very complex, and that's why from the complex dynamics you see in a real environment, in a real turbulent flow, you can obtain the solution of the average dynamic that is of course affected by all such hypotheses. Okay, what is the price of this? From an energy perspective, if we decompose the flow energy as a function of the frequency associated to each turbulent structure, we obtain a graph that looks like this. So associated with the lower frequency, so the one that are interesting in engineering, you have the major energy content of your flow. So for instance, in the application we are in mind, if we solve the average field, we can obtain the average energy of the flow, which is also the major content in terms of energy of that flow. But we lose a lot of information because instead of solving the entire dynamics of the flow, we model all the rest. So high frequency dynamics is completely missed. And of course, if you want to compute this, you cannot rely on Reynolds-Averaged Navier-Stokes equation, but you need to rely on higher order modeling and more complex modeling. But it's not the case of this project, because we are intended to harvest the major part of the flow, and so a Reynolds average approach could be sufficient for our purposes. Coming back to the Reynolds number, what's the role of Reynolds number in our input? Okay, if we increase the Reynolds number, we discovered that the flow becomes even more turbulent more and more. But the role of the Reynolds number starts to become trivial while increasing this parameter. If we look, for instance, at the drag coefficient over a cylinder, okay, this value starts to be a constant value as a function of the Reynolds number. So the Reynolds number at a certain point in application becomes is not playing any role while increasing it. And fortunately, this is the range of interest of vortex-induced vibration application, because in the case of pilot site application, in the case of application in engineering, the Reynolds number of flow is very high, so you miss the dependency of the Reynolds number while approaching higher Reynolds value. And that is a good point for modeling application, because you can consider your flow fully turbulent, you can consider your flow fully independent from the Reynolds regime, and in a certain way, this is a very good point in modeling and in numerical modeling and of such kind of applications. So that is a result in terms of average fields around an oscillating black body. So if you look at this field, it's very smooth. It looks like a laminar flow, but it's not, of course, because all this flow, it's a turbulent flow where turbulence is modeled in some way. But because the Reynolds number of the flow is so high, and because of all the hypotheses we set, the macroscopic dynamic of the flow pertaining such a system has been catched quite accurately. But of course, you miss all the high frequency related to such flow. That is not a problem because in our application, in our intention, we are not intending to harvest the high frequency, but we are intended to harvest the low frequency dynamics of such a model. Okay, moving to bluff bodies. After this brief introduction about general aspects in flow modeling, we observe that Reynolds number plays a crucial role in numerical modeling and application of fluid dynamics around objects, for instance. But we also found that the Reynolds number, the parameter pertaining to a certain configuration, becomes independent of the Reynolds number while approaching higher Reynolds number. So, what are the parameters that are important in a case of a moving bluff body? So, a body is not like this one. So, if we look, for instance, at the frequency of the oscillation, we see that increasing the frequency with respect to a reference one, at a certain moment, we change the trend of the parameter of the aerodynamical parameter around the bluff body. So after a certain point, a linear trend or a parabolic one, for instance, for the lift coefficient, is broken. So at a certain point, something happens, of course. But we see that we discussed that the Reynolds number is not is not playing a crucial role. So something else should include it into the dynamic of such devices. And this is vortex-induced vibration and what is called lock-in condition. So let me stress your attention about these parameters. So this is the so-called total pressure of a flow. So it's the summation of the pressure plus the kinetic energy associated with flow. So it's the pressure plus the dynamic pressure, so the pressure related to velocity. If you run on a bike, for instance, you feel a pressure because of the wind that is coming to you. And this is something that goes beyond the pressure, the atmospheric pressure that lives in every environment. So you can sum up the pressure of the flow, for instance, the atmospheric pressure, with the pressure you feel because of the velocity. And this is called total pressure. In a certain way, even in an unsteady scenario, this value is constant in a field. So you can consider that this value is constant in a flow field. So have a look at this. At this field. These are velocity fields around an oscillating body. And the oscillation, the cylinder is framed in different positions while it's oscillating up and down. If you look at the different position, you can easily recognize some vortices behind the cylinder. So this is the primary vortex released by the cylinder. And this is the only vortex we can resolve because all the other vortices behind the cylinder cannot be resolved because of the Rans approximation, of course. So if we look at the position of this vortex, we see that while the cylinder is oscillating, the position of this vortex changes a lot. Okay, so we see that in this case, the vortex is quite far from the cylinder. In this case, the vortex is quite near to the cylinder surface. In this case, is far again, and in this case, is near again. Okay, so these four configuration consists in 4 completely different pressure fields, but 4 quasi-equivalent total pressure fields. In fact, if you consider that the total pressure is mostly constant in flow, you can consider that associated to a vortex, there's the minimal value of pressure because the velocity in the vortex is the higher possible. So because of the total pressure is more or less constant, the total pressure is more or less constant. If you increase the velocity, the static pressure is reduced, of course. So inside the vortex, there's the minimum value of pressure. But because the position of the vortex is changing during the movement of the cylinder, this means that the pressure around the surface is changing while the cylinder is moving up and down. So if you think that in the case of the vortex very near to the surface, the pressure here is minimum, the vortex, the cylinder is experiencing forces in this direction because it follows the minimal pressure direction. So in the case where the vortex is set in this location, a net force appears from up to down. In the other case, when the vortex is set in the other position, in the top right position, for instance, a net force is appearing from bottom to up. And that is the engine that moves a cylinder like this in around from up to down in a vortex-induced vibration. So the position of the vortex behind the cylinder, it is what is pushing up and down the cylinder in its mechanics. So how to model it? So in order to model such a framework, we can consider the cylinder as a concentrated mass. This could be a clock for someone of you, but it's not. You can consider the cylinder as a concentrated mass. You can consider the cylinder linked to a stable floor in some sense, and linked to that floor with a stiffness. So there is a force that tends to stop the movement while the cylinder is going up and down. So you can consider a stiffness inside the movement, and you can consider some dissipation in the movement because of the viscous forces and so on. The system, the mechanical system where the device is installed has some internal dissipation of it. And all such dynamics, so the inertial forces related to the cylinder plus the dissipative forces related to the cylinder dynamics plus the elastic forces related to this dynamic are equivalent instant by instant of the fluid dynamic forces acting on the cylinder surface. So these fluid dynamic forces has to be determined via experiment or CFD calculations. If you determine such a dynamics, so if you compute the velocity of the cylinder, you can compute the power associated to the movement, that is the force, the instantaneous force multiplied by the velocity. So if you close such a problem, you have closed everything because you can model the power of the device without. But if Reynolds number doesn't play a role, what is playing a role in such a scenario? So including the movement of the cylinder makes the problem much more complicated in terms of non-dimensional parameter, because a lot of other non-dimensional parameters appears instantly. So you need to consider, for instance, the ratio between the density of the cylinder with respect to the flow where it's installed. So the so-called density ratio that is playing a role because, of course, if you consider a cylinder made of plastic or a cylinder made of iron, the dynamics it's completely different. You need to consider the effect of the damping forces. So you need to consider a damping ratio. You need to consider the effect of the elastic forces acting on the cylinder, so a sort of reduced stiffness. And you also need to consider the effect of time scales. So the effect on time scales allows you to define two parameters, the reduced velocity and the Strouhal number associated to the body movement. So the reduced velocity is, in practical terms, the ratio between the time scale associated to the natural movement of the cylinder, that is the frequency of the cylinder, and the convective time scale. So the time scale associated with the convection of the flow. While the Strouhal number associated to the cylinder dynamics is the time scale associated to the convection, again, ratioed by the time scale associated to the body movement, not the natural frequency of the cylinder. So the Fy and the Fn are completely different parameters. The Fn is the natural frequency of the system, so it's the frequency that the system show when it's perturbated in a vacuum environment, for instance. So if I perturb this table has its own natural frequency because it starts oscillating with its own frequency. Instead, the frequency, the Fy, is the frequency related to the body movement. So it's something that could be present even in case of a forced environment. If I force this table to move in a certain way, this table starts to move with a frequency that is the one associated with the force I'm applying to that table. So these two parameters are completely different parameters from a physical point of view, but they are both time in terms of scale. And so you can, in a certain way, compare the time scale associated to the inherent characteristic of the body, so the frequency associated with its natural characteristics, with the time scale of the flow. And you can compare the frequency related to the body movement, again, with the time scale of the flow. And you obtain such two very important parameters in Vortex-Induced Vibration, that is the reduced velocity and the Strouhal number associated to the body motion. Okay. So when a system like that is able to produce energy at the end, it's able to produce energy only when the frequency associated to the body motion it's equal to the frequency of the system in its in intimate characteristics. So in a non-dimensional path, when the Strouhal number associated to the body motion is equivalent more or less to the inverse of the reduced velocity. That means that these two frequencies becomes the same number. And we measure this in a virtual environment because we plot the reduced velocity, the Strouhal number as a function of the reduced velocity. This is a branch of a parabola in a mathematical sense. And we see that all simulation collapse to this branch of the parabola in a certain range of reduced velocity. Outside of this range, something else appears. So instead of following such a dynamics, the Strouhal number associated to the body motion follows the Strouhal number associated to the vortex shedding. So the vortex shedding has their own Strouhal number. That is something specifically related to the geometry. If you have a cylinder, you have a specific Strouhal number for the vortex shedding. If you have a square, you have another number, and so on. So if you look at the Strouhal number outside this specific range, the Strouhal number associated to the body motion collapses to a Strouhal number associated to the vortex shedding. So you are outside of the locking state. And this value, so the value of the Strouhal number associated to the vortex shedding, mildly depend on the Reynolds number. So in case of higher Reynolds number, so in case of higher reduced velocity, in some sense, you see that the Strouhal number associated to the body motion is the same number for every configuration, because the Reynolds number is not playing a role anymore. If you look at a lower reduced velocity scenario instead, you see that there is a mildly dependent on the Strouhal number associated to the body motion with respect to the reduced velocity, because the Reynolds number is playing some role, because the flow, in some sense, below a certain value of reduced velocity, it's in a transitional state. So it's neither laminar, neither turbulent. What is very interesting of this dynamic, that this dynamic is very regular. So you can tune your clock with this dynamic, because the frequency associated to the body motion in a locking state is very confined to a precise frequency. In fact, if you compute the Fourier transform of the vertical displacement of the cylinder, you obtain very confined frequency associated to each body motion. So you can easily model the body motion as a single harmonic function. So it's a monochromatic approximation, of course. So the body motion can be easily modeled as a function y in terms of the time that is equal to an amplitude times the sine of 2 pi fn times p. So you have a very straightforward approximation of the body motion in a vortex-induced vibration device, because the frequency associated to the body motion has a unique harmonic. But the problem of this scenario, what's the problem of this scenario? The problem of this scenario is this formula. Frequency is an inverse of the time. And I want to stress your attention about this, because in order to catch low frequency, you need to catch very high, very long time window. Because we look at the beginning, I told you that we are interested in low frequency dynamics. And so in order to catch low frequency dynamics, because of the definition of frequency, you need to protract your simulation or your experiment for a long time. And this could be an issue. It's an issue in simulation, and it's an issue in experiment. You need to be very aware about the steadiness of your experiment or the steadiness of your simulation. But steadiness here is something weird, because nothing is steady. So you need to be aware about the statistical steadiness of your environment, so simulation or experiments. And simulation are not very prone in this, because from my experience, in order to tune the database behind the vortex-induced vibration device, you need to make simulation very long. You need to take simulation for days even. And in particular, with De Vanna, we perform simulation around 2065 core hour of simulation. That means that if every simulation takes more or less 3 days to be completed, it means we count that we did as 3,700 simulation for this problem. And increasing the core of each simulation is not playing a role, because if we For instance, if we look at the time we require for each simulation, and if we double the computational resources associated with each configuration, there is no speed up in terms of time to solution. So two-dimensional Ran's equations are not prone to scale on CPU's environment. ANSYS Fluent doesn't not scale very well in such a scenario. So that's it. And I hope that experiments are faster than this. Some results. So in order to convey results about vortex-induced vibration, you need to separately study the role of all the parameters related to such a dynamics. And in order to make results as general as possible, you need to make parameter. You need to perform simulation, and you need to fill the database in a non-dimensional way. So the first parameter you need to consider is the density ratio of the system. So the ratio between the solid density, so the density associated with the cylinder, for instance, and the density associated with the flow. If you look at the root mean square of the vertical displacement made non-dimensional by the cylinder diameter, you see that the vertical displacement peak in a certain range of reduced velocity. And this is a symptom of the locking state. But there is a mild dependency on the density ratio because of the low Reynolds regime, of course. So if you look at the left branch of this curve, you see a mild dependency of this curve with respect of the density ratio. And this dependency is completely loose if you increase the velocity, that in a certain way means increasing even the Reynolds. This results is this more or less the same if you look at the Strouhal number associated with the body motion with respect to the reduced velocity. And we also detect the vortex-induced vibration, the locking state around this branch of hyperbola, the theoretical trend, so the ones you can compute by hand. And what is very interesting for our application is the root mean square of the device efficiency. So you can take the ratio between the power associated to the body motion and the power that the flow has by itself, because the flow, because of its kinetic energy, has its own power. So if you take the ratio between the power of the body motion and the power associated to the flow, you can get the root mean square of the efficiency, so the average efficiency of the device, that in a certain sense in the locking state is around 0.1, 0.2. So you can harvest more or less 0.1, 0.2 the entire content of the flow energy. And there is a mild dependency on the density ratio, because this value, so the higher value of the root mean square of the efficiency pertain to the lower reduced velocity range. So because of the reduced velocity range is also associated to low Reynolds number, there is a mild dependency of the reduced ratio. Role of the stiffness. So if you look at the role of the stiffness, this is much more compact compared to the role of the reduced velocity. So moving the reduced stiffness in a wide range, you don't see appreciable differences with respect to the stiffness. So what is the role of stiffness in general? The role of stiffness is this one. So if you tune the stiffness and you plot the displacement as a function of the Reynolds number, you see that curves moves from left to right, more or less in a solid way. So there is a shift of the curve as a function of the reduced stiffness. So you can tune the stiffness of your system as a function of the Reynolds number of your flow in order to catch the position, the stiffness you need in order to maximize the amplitude of the device as a function of the Reynolds number of the flow you have. And these results as another implication, another important implication, because we plot the root mean square of the displacement as a function of the Reynolds number, we saw that the results are not collapsed over the same curve, which is what happened instead plotting the same results as a function of the reduced velocity. So reduced velocity in such a scenario, in such a device, plays a very important role because it's the intimate self-similar parameter that governs this dynamics. If you plot everything as a function of the reduced velocity, everything collapses to a single non-dimensional ideal device. And this is a very good property of this parameter, not in general for such a results, but in general for the inverse transformation, because if from a modeling perspective you are interested in collapsing the curve, and from an applicative perspective you are interested in the inverse application, so taking the collapsed curve over a realistic scenario. So inserting your boundary condition, inserting your flow velocity, your cylinder diameter, and so on, and take this value of reduced velocity, this one, in an opposite sense. So from all the collapse curve, obtain your specific device. Damping ratio. Damping ratio is associated to dissipative characteristics, and in particular, all the system has their own dissipation side. So you can model dissipation as a physical dissipation ratio by the critical dissipation that is an inherent property of a system. So it depends on its mass and its stiffness. And if you look at the displacement Strouhal number as a function of Strouhal number associated with the body motion over the root mean square of the efficiency, while increasing the critical damping, while increasing the non-dimensional damping, the locking state becomes narrow and narrow. Okay, so you can obtain the locking state in a shorter range of reduced velocity. And this is a very crucial results from our application, because dissipative forces are inherent in our application, are the one associated with Marco will say after, I think, associated with the generator. So a generator, because of their resistive characteristics, poses some dissipative forces inside the system. So we need to tune very carefully such a parameter in terms of the whole system, because if we move through too high damping ratio, the locking state disappears. To conclude, having a database like that, we can plot all the results as a function of the reduced velocity. And for instance, plotting the root mean square of the efficiency as a function of the reduced velocity. If you see all the data we obtained, so all the simulation we perform, all the data we were able to collect, collapse over a same curve in terms of root mean square of the efficiency. So a part of the scattering related to simulation and the uncertainty related to CFD that are all the results collapse on the same curve. So you have a map in order to tune your device that is fully non-dimensional. And from this map, if you know the characteristic of the incoming flow related to your device, you can multiply the power associated with the flow you have with the root mean square of the efficiency at the specific reduced velocity you are intended to design your device. And so you can compute directly from such a map the power extracted by the device. So, to conclude, vortex-induced vibration represents a viable alternative to recover energy from water sources that are difficult to exploit in a different way. Theory is lacking of simple models, and in order to determine a simple model, I think you need to think in this way. So you need to think in a non-dimensional way in order to collapse all the results over a single curve. And then if you want to design a specific device, you take the curve and you take the inverse transformation in order to get your specific design. Vortex-induced vibration, even being something related to a single phase flow, so in principle, something regulated only by the Reynolds number, because of the introduction of the movement of the body with respect to the flow and so on, depends of many other non-dimensional parameters, the density ratio, the reduced stiffness, and so on. So this number is huge, and in order to determine the result of each parameter, you need to perform a lot of input simulation or experiment. But fortunately, some self-similar properties connect all such parameters one to each other, and this is a very good property of this system that makes vortex-induced vibration feasible in terms of its design. So with this, thanks for you.